Okay, someone that had x to the fourth, what did you guys get? 4x to the third. Thank you. Very good. Okay, who had x cubed? What did you guys get? Did no one have that one? What letter was that? K through? No, that was. Yeah. No one had that one? Oh, I didn't hear it. I'm sorry. Okay, sorry. 3x squared. I just didn't hear you. I'm sorry. Okay, and then did anyone have x squared? But that goes to 2x. Okay, did anyone have, this was supposed to be the shortest one. What'd you get? 1. Okay, that's all right. Good. All right, so some of you already know this shortcut and have been like trying to use it to check yourself. So if you don't know it yet, though, I want you to try to look at the pattern of all these derivatives in a row. So these were my original equations, just like counting up by each power. If you think about the exponent to each of these, this is like 1, 2, 3, 4, and 5 here. Where do we see the numbers 1, 2, 3, 4, and 5? In the front, the coefficient. Good. So when you take a derivative and you're doing all your like x and delta x and h, all that stuff, in the end, when you simplify, it always works out where the power becomes the coefficient. So there's that pattern. And then also, if I look at the exponent here, this is a fourth power, third power, second. This counts as a 0 power because there's not an x there. So if I look at the pattern of the exponents, what happens is I reduce the power by 1 to get the new power. And that is a shortcut called the power rule that we're going to learn today. One of many rules we're going to learn that you can use as a shortcut. Now, you still have to know like the long method that we've taught and we've spent 3 days learning. But this is a shortcut method where now, like if we don't say you have to do it the long way, now you can just do this instead. Okay, so let's kind of clarify what a power rule means exactly. And this is not on your paper and we don't have to solve this out, but this is just like, okay, how does a power rule look on more complicated expressions? We're going to talk through ones that get more and more complex also. So I know you guys have probably noticed that x squared goes to 2x. So you probably have already kind of noticed the power rule, but didn't maybe think about some more like complex powers. How is that going to work? And we're going to talk through things that get like more and more kind of difficult for power rule. Okay, so this should be the start of your notes now. So just check you're on this side. There are like more than 20 derivative rules that we're going to learn over the next like 3 to 4 weeks. Today we're learning, I think 7 of them. 7 of the 20. That's probably more like 25. So this is the first of our derivative rule shortcuts. We're going to learn all these rules so we can avoid having to do that every time. Avoid having to do the delta x and h process. So first of all, first rule is this one. It's an easy one to remember. The derivative of any constant number on its own goes to 0. The reason why is because if you have a constant number, so let's say I had y equals 5, the graph of that is a horizontal line at 5 or whatever the number is, and derivative means slope. So this means derivative. If I'm saying what's the derivative of that constant number, that's the same thing as saying what's the slope of that line. And the slope of this line is 0, 0, 0, 0, 0. The entire slope is always 0. And that's why the derivative is 0. And that's true no matter what number you choose. If you do y equals 2, still 0. Y equals -1, slope is still 0. So any constant on its own will go to 0. So that's the first rule. Second rule is the rule that we just kind of went through and looked at. If you have x to a power, this power, you bring in front to make the coefficient, and then you subtract 1 from the power. And that's the one that some of you had hinted at possibly knowing, even called the power rule. Bring the power in front, subtract 1 from the power. The second one. Or no, put your computer up. Boys, put your computer up. Thank you. Okay, then third rule is called the constant multiple rule. And that rule says that, okay, if I have a constant that's not just by itself, it's a constant times some sort of variable, whether it's a whole equation or like an x squared, like constant times something. In that case, the constant stays with the problem and you just take the derivative of the equation or the variable part. I'll show you an example of this, but I'm just trying to show you like this derivative does not end up being 0 times something else. Like when you take the derivative of a constant by itself, it's 0. But when you do the derivative of a constant times something else, is the constant multiple rule, and the constant stays with the problem. I'll show you what I mean by that here in just a second. And then this next rule should just kind of make common sense. So like if I have a whole equation with things added or subtracted together, I can take the derivative of each part of the equation and still get the answer. That will just be kind of like a common sense. It'll just kind of flow that way naturally anyway. Okay, and then our last three, let's put a 7 here, 5, 6. Like this is a different rule than that rule. Okay, so for trig rules, sine and cosine. The derivative of sine goes to cosine. It's really interesting to kind of think of that. So like this slope of sine at any point along the graph is the same thing as the cosine graph. It's kind of cool. Like sine goes to cosine. And then cosine, its derivative is actually negative sine. So it's a little tricky to remember that negative in there, but cosine goes to negative sine. And then this last one, the derivative of e to the x is e to the x. E to the x looks like this. And if you think, how could it be possible for an equation to have a derivative that's the same thing? Remember, your derivative stands for slope. And my slope here is like really flat at first, and it gets steeper and steeper and steeper. And if I was to graph those numbers, I would have like low numbers and then higher, higher, higher numbers. And so e to the x does go to itself. E to the x goes to e to the x. So easiest derivative ever is e to the x.
It's the same for the log.
It's not the same for log, and that'll be a different rule. We'll learn a different day. Good question. So like I said, there's probably 20, I don't know the exact number, 25 maybe rules. This is the first 7. And then some of them are going to be logarithms. Some will be the other trig functions. We'll do inverse trig. We'll do stuff multiplied together, divided, composition, like got a lot of rules. A lot of rules coming up. Okay. All right. On the next part of your notes, this is just an explanation. We just pulled 2 rules at random and said like, okay, so you don't have to just believe us. Like, here's why this rule works. This is like a college class, right? AP class is college expectation. And a lot of times in college, the professors will focus on the proof of every rule, the explanation on why every rule is always true. I'm not going to focus on this a lot. I'm exposing you to it so that you have seen a proof before. You do not have to memorize this. It's just an explanation on why these 2 rules work. So just as an example, the constant multiple rule. So pretend this is my original equation, f of x. My definition of a derivative says do limit as delta x goes to 0. Plug in x plus delta x to the original, then subtract the original all over delta x. It's like we've been doing this hardcore like the last couple of days a lot. Well, then if I have a c in both terms on the top, I can just take that out as a greatest common factor. And then based on my limit properties, I can pull the c out front. And what I'm left with is definition of a derivative, which we can just call f prime. So that shows us that rule will always work. You always will be able to just like factor that constant out front. Question?
Just give
We will. Yeah, we're gonna do lots of these. Like, I'm gonna example you to death after this. Yes. Yeah. Okay. Second one. Like, why does the sine rule work? Okay. So start with the equation sine. If I plug in my definition of a derivative, so limit as delta x goes to 0, I take x plus delta x. I plug it into the original equation, then I subtract the original all over delta x. I think, oh, what in the world would I even do with that? Last year, you did some of these trig identities with sine and cosine. We have 2 things added together. You do sine of the first, cosine of the second, plus cosine of the first, sine of the second. That was one of your last year's identities. So from here to here, do an identity, and then copy down the minus sign and the delta x. And then from there, if you regroup, there's 2 terms that have a sine x, this one and this one. So if I kind of group those together and take out a negative sine x, I'm left with 1 minus cosine, carry down the last term. And then this part is one of my identities I learned in chapter 1, that goes to 0. And this part is one of my identities in chapter 1, that goes to 1. So I end up with 0 plus 1 times cosine, which is cosine. You do not have to memorize that, but now you can be like, oh, yeah, sine's derivative is cosine. Yes. Okay. Because of all that. And you don't have to do all that. You just now can just remember sine goes to cosine. Okay, so let's do lots and lots of examples to practice these 7 rules we just learned. So flip to the other side. Okay, so first example, this is a constant number all by itself. So the derivative of a constant number, do you remember what that goes to? 0. Yes, good. Okay. F prime of x is 0. Very good. Constant number just goes to 0. So slope of that line would be 0. On number 2, I have a linear. Remember, derivative is just the slope. So just thinking ahead for a second, I know my derivative here will have to be 3 because that's the slope of this linear function. But let's talk about it in the context of the rules that we just learned. So this is a constant times a variable. So this is my constant multiple rule. That means 3 is going to stay with the problem. And then I just do the derivative of this part. That counts as x to the 1. So that becomes 1x to the 0. I bring the exponent to the front. And then I subtract 1 from the power. So I get 1 x to the 0. And then x to the 0 is 1. So this part just turns into a 3. And then the minus 1 is a constant that's off by itself. And the derivative of a constant, 0. So that's how I end up with just 3. But since it's a linear function and I know the slope of that line is 3, like I already could have just known derivative was 3. Okay, third one. So this is also constant multiple. It's 2 times a variable. So I keep the 2 there, and then I'm going to do the power rule. And if you want to kind of do this in one step, you could go ahead and make that as 6x squared. Because I keep the 2 there, and I bring the 3 in front, so 3x squared, and then the 3 and 2. And then this will be minus 2x. And then this is x to the 1, so this becomes plus 3x to the 0, which is just 3. And then e to the x just stays e to the x. So I'm going to have minus e to the x at the end. Okay, number 4. So f prime of x. We start out with a constant first. So like this 5 plus, the 5 part goes to 0. Because that's just a separate constant that's added. It's not multiplied in. So this part goes to 0. Sine goes to cosine. So this answer is cosine. Okay, question number 5. It looks a little bit weird because of the pi symbol. Remember, pi is a number. That's 3.14. But instead of like writing out all the decimals, we're just going to leave it as the pi symbol. So I bring the power to the front as a coefficient, and it'll be pi x. And I subtract 1 from the power, pi minus 1. Instead of putting 2.14159 up there, just put it as pi minus 1. Bring the power in front, subtract 1 from the power. All right, then 6 has a pi in front, but it's times cosine. That means it will stay with the problem. It's a constant multiple. That doesn't go to 0. Let's keep the pi. Okay, and then do you guys remember derivative of cosine? Negative sine, perfect. Okay, so f prime of x is negative pi sine x.
Yeah, can you explain one more time why the pi stays?
Yes. Yep. Okay, so the question is like, explain one more time. Why does the pi stay with the cosine? And it's because it's multiplied. If it had been pi plus cosine, this would have gone away. But if it's multiplied, it stays with it. Okay, then, okay, we're about to take a jump up in difficulty level here. So then like, okay, now it's a little wacky with some fractions in here. So please add yourself a note. Maybe we can fit it on this side. If you have x in the denominator or within a square root, You have to rewrite the expression first. I will show you what I mean by that. Okay, so the rule x to the n, that derivative rule is very, very specific. It does not work if your x has something in parentheses, or if it's in the denominator, or if it's times a cosine, or like, it only works if you have x to the n power. Now you can have a constant out here, that's okay. But that's the only exception. It can either be x to the n or a constant times x to the n. So this problem is one where I'm seeing x in the denominator. This rule does not work with x in the denominator. It's got to be x to a power. So before I can start doing my derivative, I have to rewrite first. And here is how we would rewrite this one. Is first I would get the parentheses gone. The squared applies to both of those. Then I would rewrite the exponent by taking the x that's in the bottom and just moving it to the top and changing my exponent to -2. And I now have a constant times x to a power. I'm not allowed to divide by x or like have x times something or in parentheses. That's just simple, only x to a power, which that's what I have right there. So now that I've rewritten it, now I can go to my derivative step and say, okay, well, my derivative then is power rule. I'm going to bring the exponent in front. That becomes -4/9. And subtract 1 from the exponent. A little tricky with negatives. -2 minus 1, -3. And then I would just move that negative power back down. So -4/9x³. And that would be your answer for derivative. Okay, number 8, similar idea. And let me show you, it's very tempting to look at this and skip that rewrite step, but if you do, you won't get it right. So I might look at this and be like, ooh, it's pi/6x. But it is not that. You cannot take a derivative of an x in the denominator. You've got to rewrite your expression first and then go through and do your derivative. So this is going to become pi/3, and I'm going to move the x up, so x to the -2. Which is not my derivative, that's just rewriting it. But now to take the derivative, I can do the power rule by moving the -2 in front. So -2 pi/3. And then when I subtract from the power, I'm at -2. Now it's going to go down to -3. So -2 pi over 3x³. Yes.
So should the answer is -2. And then x to the -3. Would that be acceptable?
Okay, so the question is, can you leave a negative power in there? I mean, technically, yes. We're not going to make you simplify a ton in general, like fractions, and we talked about not rationalizing and stuff. This is technically the right answer. But pretty much any of if you're doing a multiple choice answer, a negative would never be left in there. Like we might leave something unrationalized, but usually a negative power is brought back to the bottom, and that's just because it started like that. So we just made our answer look like how it started. But you are correct. So technically, you'd have been correct at this step. Okay, number 9. Will you please put a star by number 9? This one. All right, you are going to get one like this on Delta Math. We're gonna get one like this. It's so easy to get stuck. Okay, it does not equal this. You are not allowed to do derivative on top, derivative on bottom. Doesn't work. We have to rewrite first. So like, it's very tempting and everyone will probably do that at least once and be like, what am I doing wrong? And I'm gonna say, ooh, go to that star problem in your notes. If you have an expression like this long equation with x on the bottom, you have to rewrite it first. You gotta rewrite it first. So there's two ways you can rewrite it, and I like to do, I call it bunny ears, even though there's like three things here. If I regroup like this as a fraction, oops, sorry, 2x squared over x, and then this as a fraction, and then this as a fraction. I know that's not actually bunny ears. Bunny ears would just be 2 ears. This is like a genetically mutated bunny with 3 ears, or maybe we'll call it a crown. I don't know, but I like to split up that way. There is another way to do it, which I'll show you, but you just keep the same denominator and split your numerator apart. And that is totally legal. You can split a numerator apart like that as long as you keep the denominator. And then, so this isn't the derivative yet. But then I can simplify that and get 2x minus 3. And x cancels there and x cancels there. And then I would call this x to the -1, which isn't my derivative yet, but is now in a format that I can take the derivative of. I've got a constant times x and a constant and then x to a power. So my derivative for this one would be 2x will just go to 2. This -3 is a constant, so that will go to 0. And then power rule here is going to be -1 x to the -2. And so I would just call that 2 and then -1 over x squared. So really quick, just before we flip over, if the bunny ears method doesn't make sense to you, another way you can do this is take the x up as a -1 and then distribute that in to here. And when you add exponents, you'll get this exact same thing. So like the -1 subtracts 1 from the power here and here and here. So you can also just bring out the denominator and distribute it if that is helpful. Question.
Could you do like after you simplify or you also 2x and then 3 plus x to the -1 to you go to the answer again from there?
Yep,
Thank
sure.
you.
Yeah, for sure. Okay, so 2x, that derivative goes down to just a 2 because it's like x to the 1. I bring the 1 in front, which gives me 2, and then x to the 0 goes down to 1. And then this one is a constant, so that goes to 0. So that's gone. And then this one, I bring the -1 power in front, and then subtract 1 from the power gives me -2. So it's just like each individual piece. And then move the -2 down.
Thank you.
You're very welcome. Okay, you ready to flip the page over? Or, oh, no, never mind, it's not flipping. Okay. Sorry, last page though. We have lots of examples today, death by examples. Okay, number 10 on this side has square roots, and that's another case where you have to rewrite before you can take the derivative. So I'm going to rewrite, if this is a cube root, I can rewrite that as x to the 1/3. And if that's a fifth root, I can rewrite that as x to the 1/5. Question?
I have a question in the last.
Okay.
So I'm using this like 2 minus 1 over x, but like.
What was it, x or squared? I thought it was squared. I thought
Yeah,
it was squared.
minus 1 over x squared.
Yep.
And I was wondering why there's minus instead of plus.
Okay, so this came from, it was x to the -1 originally. I brought the -1 in front, which then made that a -1.
Okay.
Subtract 1, and then the negative just is there. I'm sorry, I didn't mean to go over that. Too fast? Yeah, definitely speak up if I'm going through something too fast. It's like the third time I'm saying this, so I might just be zipping through thinking everything's good. Y'all gotta stop me. Okay, so we're doing a radical can be the same thing as a power. So like I bring that root up and root up. And then of course, e to the x is just like its own thing. Just gotta make sure you don't forget it. It's easy, but we can't forget it. Okay, so that's the step where I rewrite it. Then when I go to take my derivative, I'm gonna do the power rule, and the power rule, it's got lots of fraction action. Because now I gotta do 1/3 minus 1. Which, okay, seems like it should be easy math, and it is, but like, how do we think through that in our head so we can learn to do this quicker? So whenever you're subtracting one, instead of saying the number one, go ahead and make it whatever this denominator is. So like in my head, I'm gonna be like, what's 1/3 minus, instead of 1, I'm gonna call it 3/3. And then 1 minus 3 is -2. So this power ends up being -2/3. And then I have the 1/5. When I bring that in front, 1/5, x to the, okay. Now I'm doing 1/5 minus 1, but instead of calling it 1, I'm going to call it 5/5. So 1/5 minus 5/5 is -4/5. You're going to start to get really good at fractions after this chapter. Question from theory. Oh, what is it?
I just think that it's the remaining part of 1/5, the negative sign part. Or like the remaining.
Sure, I get that. Okay, so excellent suggestion. So, thinking of fractions, the suggestion was like, oh, there might be an easier way to think of that. If you think of, I don't know, like 1/5 of something, the rest of that is 4/5. It's like the remaining of the whole 4/5 would make a negative. Now, the only thing I will say is sometimes you'll get powers that are more than one, like maybe you have a 7/2 power or something. So that would be a little bit harder, but yes, definitely. Good suggestion, good idea. E to the x goes to e to the x. And then I would just rewrite this as 1/3 x to the 2/3 plus 1/5 x to the 4/5 plus e to the x. And that answer is totally fine. You could also just, by the way, make this cube root of x squared if you wanted to, or if there was a multiple choice question that was written differently, know that these are the same. Remember, the denominator is the index of the root. This could be 5/5 root of x to the 4th. The denominator is the root. Yes, question.
Then what happened to the coefficient?
Oh, it's still there. I'm just saying just that part of it. Yeah, like instead of x, if there was a radical, like cube root x squared, that would be the same thing. Okay, so those are some hard examples. Everyone bearing with me so far? Yeah? Okay, all right. You guys tell me what 11 is. Think through it for a second. I'm hoping these are ones we have memorized already. Okay, so f prime, what's 2 sine go to? 2 cosine, good. Okay, so the 2 stays with it, good. Okay, very good. What does 3 cosine go to? -3 sine, good. Okay, and what does 1 go to? 0. Good. So that one's just that. This might be the only time in your life where trig is potentially easier than not trig. Like there's no fractions in there. It's just sine goes to cosine goes to negative sine. So yay, bringing trig back. Okay, we have 2 last like applications to talk about. Do we need a little breather, like a little break? Yeah, okay, I'm seeing some yes. Okay, let's just do like a quick 30-second. Move your arms around. I don't know, stand up, get a drink of water. Just quick break. We'll regroup.
Like, and then when I know. Oh. When it came out of the bank. And when I got the house.
Okay, all right, let's go ahead and finish. I think there's just 4 problems left. They're just a little bit more like thinking, but. Okay, next topic it says find the point at which the function has a horizontal tangent. So this no longer starts out just saying that find the derivative. Okay, so it's not just like find the derivative. There's more to this, but it will use the derivative. And I'm gonna focus on this word. Okay, so that word alone tells me slope of 0. Everyone able to look at that word and say, okay, slope 0. Well, we now just learned this week that the derivative is the slope. Okay, so this is telling me take the derivative equal to 0. And then answer as a point. So those directions are saying take the derivative equal to 0 that's where you'd have a horizontal spot. And just make sure your answer is written as a point, like a location of where that occurs. So now we have shortcuts and we don't have to do the delta x thing every time. And so this derivative just got very easy, just 2x. Again, power rule, and that goes to 0. So now that we have these shortcuts, these problems aren't quite as long. Like I'm not having to do all the other stuff. So I could just take my derivative equal to 0 and solve. And then I just make sure that my answer is a point. So I have x equals 0. Where do I get the y value? Plug in. Yes, great. Okay, where do I plug in? The original. Yes. Okay, so tempting to like plug in here. By plugging in the original, you get your point. Your y value is an original function. So I plug in 0 up here, and I get 1. And then just for funsies, let's think about x squared plus 1. It would make sense that at 0, 1, that's the spot that we're horizontal. Because x squared plus 1 is quadratic up 1. So that makes sense that that's the location. Okay, number 2. Okay, help me out with my derivative. What's my derivative on number 2? 3x squared, I heard it, plus 1. Very good, good job. Okay, so that's my derivative. I want a horizontal tangent, so I take that equal to 0. I'm going to subtract 1, divide by 3. Oh, I'm hearing people discuss like plus or minus, but do you see the imaginary come up there? Oh, the second I see it, I'm like, nope, no solution. We don't do imaginary calculus. So square root of a negative, we don't do. We just say it does not work. And that means my graph, whatever this cubic looks like, my squiggle that's in there just wasn't a very big squiggle. It just didn't totally level out before it went back up. It just kind of like did just little, like just a little squiggle, not enough to like go horizontal. And so that's why my answer reflects no solution. All right, then number 3. Okay, help me with the derivative. What do you get for the derivative? E to the x minus 1. Good job. Okay, minus 1 because that goes to like x to the 0. And e to the x, of course, just always e to the x. All right, when I put that equal to 0, I move the 1 over. And then, yeah, so swish and flick. Is anyone thinking that? Okay, that was yesterday's lesson in math 3, if you missed math 3, but I don't think, like, I look at that and I say, oh, e, to get rid of an e, I do an ln. Like if there's an ln, to get rid of that, I do an e. So when I look at this problem, I think ln, but swish and flick also works. You want to just switch the form. If you ln on both sides, those cancel. I don't know how you switch them. I just know that people do it.
Yeah.
I actually don't know what it is.
You go through the.
Yes, I think she did a wand yesterday. It's a whole like Harry Potter thing. Yeah. I would just ln on both sides if you don't know what that is. I think math teachers probably all teach that slightly different, but the opposite of e is an ln, the opposite of ln, power of e. Okay, then ln of 1, just really quick. We have to know that ln of 1 is 0. So this actually equals 0. L of n is a number, it's 0. And then we plug 0 back into the original. So plug 0 back into the original to get the y value, which is 1. Yes, question.
How is that?
I don't know. Okay, excellent question. So the question is like, how is that graph gonna have a tangent? I honestly do not know what that graph looks like either. That's not one we have to memorize. Shall we look at it real quick? E to the x minus x, right?
Yeah. Yeah.
Okay, so e to the x, I think we all know what that one looks like, but if I put a minus x in there. Interesting. Okay, so horizontal tangent right there, the 0, 1. Correct. Yes, okay, so then there was a follow-up question. Well, wait a minute, what if it was just e to the x? You would get it does not exist. Because the derivative of that is e to the x, which doesn't ever equal 0. This horizontal asymptote over here, so it never equals 0. Excellent questions, guys. Is that the last of that time? Okay. Okay, so horizontal tangent in summary is derivative equal to 0. Derivative equal to 0. All right, then our last notes example today is another one where we haven't seen directions like this, so we're going to just dissect the directions really, really carefully. Within the first 4 words, I see this. Use the tangent line. Pause for a second. I already know I need point and slope. Okay, do those words just like pop up in your mind now when you see tangent line? It means point slope. They don't? Okay. We're going to eventually. Oh, because you don't have, yeah, we're working on it. Good point. It didn't say write the equation of. Proof says use the tangent line. Okay, true. I get that. But we do see like use the tangent line. So if I don't have the tangent line, then that means I gotta write the tangent line. And so point slope. Okay, then I see at x equals 3. So far that tells me this. Okay. Then I see these words like to approximate f of 2.9. Right now, like what is this? Question mark. Okay. We'll figure that out in a second. If, and then here's my equation. That's the equation right here that I'm going to use to get the y value. So I'm going to go ahead and do the part I do know. And once I have what I do know done, then I'll see if I can't figure out what I'm supposed to do with those words. So let's look at the part I do know. I plug in 3 to the original. So 27 minus 2 is 25. Am I able to get the slope from that information? Slope is, I heard it, derivative. Yeah, I just say the derivative. So I do f prime of x is 6x, the minus 2 goes to 0. And now that I have the derivative, if I plug 3 into that, yes, I can get the slope. Question. Yes, okay, so I plugged in 3 to the original equation. So 3 times 3 squared minus 2, and then just did that math. So 9 times 3 is 27, minus 2 is 25. Once you have point and slope, you can go ahead and immediately fill in your equation. So y minus the y coordinate equals the slope times x minus the x coordinate. Okay. I got that. I got that. Use the tangent line. Okay, so I did this, and I'm going to try to do some sort of like context clues. Like when you're reading difficult text, you just try to use like the rest of the sentence to figure out what to do. Okay, so I have now a new equation, and it says use the tangent line. X, so I'm going to use this to approximate, and I'm like, well, what does this mean? F of 2.9, that means plug in 2.9 for x. So these directions are saying use the tangent line, plug in 2.9 for x. That word approximate, we haven't done a lot of yet. It will become something that we do a fair amount of, but it means you're approximating kind of like what the y value would be on there, but using the tangent line instead. And we'll get more into the word approximate later. But from the context clues, I can tell that I'm plugging 2.9 in as the x value. So 2.9 minus 3 is negative 0.1. So y minus 25 equals negative 1.8. Just move the decimal. And then let's see, add 25, 23.2. And so your answer on this one isn't like a point, isn't a slope, isn't a tangent line. It's what you get if you plug 2.9 into the tangent line. Now use the tangent line with an input of 2.9.
How can you use like approximately?
Well, so what we're doing, so this is the value on the tangent line. And then when this word approximate means we're approximating that. So you are going to use an equal sign here. But then, like I said, later on, when we do more of this approximation stuff, it would have been like that this f of 2.9 is approximately. It's not exactly 23.2, because if I plug 2.9 in there, it's not exactly that, but. Like I said, the word approximate we'll do more of later, but I want you to be able to read that problem and see that this is saying plug in 2.9 as x. Like that's what that's telling us. Okay, so that's our shortcut. Or our 7 shortcuts for today. Okay, for the rest of our class period today. So we are here on our list, okay? Right now, we're gonna spend some time. It is currently, it's currently 12:46. So we have 38 minutes of class left. I need the last 10 to 15 minutes of class to get started on tomorrow. Okay, just because tomorrow's a lot. And so like, we're gonna spend what's the difference? 20 some minutes now on these things. So you have time now. There's not a new Delta Math up for today. It's like just recycling yesterday's Delta Math because we're going to be off by a day. So use your time now to work on WebAssign and or Delta Math and or FRQs. And then in about 20 minutes, I'll be like, okay, pause. We're going to work a little ahead for tomorrow. So tomorrow is not as bad. Okay, so you can work on any of those things. Yes. Yes. Yes, I'll show that. That's a good point. I will show which ones. Yes. Oh, no, that's.
Oh, yeah.
Yes, you may.
That's